All right, this objective 5.1 is to make approximations to nearby known values using tangent lines. So this first video is going to focus on creating tangent lines and using them to do this. And then the next level is going to be to determine if your estimation is an over or underestimate. So just so you have an idea of what we're talking about, if you had some line that had a point and you drew in a tangent line to that point, you would get like a straight line that kind of looks like that. And what you notice is, well, sorry, it's supposed to be straight. What you notice is that if you like zoomed in and looked nearby to that line, that the y values of the blue tangent line and the black values of the black, or I'm sorry, the y values of the black actual function are probably extremely close to each other. So the blue line is a good approximation for the black line in nearby values. As you get farther away, like here, probably not as good, and here not as good, or at least like not reliable. Most of the time this isn't super helpful because if you know the function, then why would you need to do this at all? But there are situations in which you might know the slope but not the function itself. So even though we're going to be using functions, it's kind of for those situations that we're learning this. So in your page it says it starts with practicing finding tangent lines. This was an objective from earlier in the year, and here's just a reminder of point slope form. We're still using that. In this first example here, we've got x equals 4. We can find y by plugging in 4 into the function. So that's going to be f of 4 is equal to 3 times 4 squared minus 1, which comes out to 47. And then our slope, of course, is the derivative at 4. So really quickly, I'll take f prime of x, which is 6x. Which means that f prime of 4 is 6 times 4, which is 24. So our equation of our tangent line is y minus 47 is equal to the slope, which is 24, times x minus 4. Totally review, this is an older objective. I've got another example of that. This is an actual AP question, so I wanted to throw it in here. They ask for the same thing, except they don't give you an x value at all. They say at its point of inflection. So the first thing we need to do is find that point of inflection. In order to do that, we need to take our derivative twice and set it equal to 0. So y prime is equal to 3x squared plus 6x, and the 2 is gone. And y double prime would equal 6x plus 6. Sorry, equals. If we set this equal to 0, you're going to get very quickly that x equals -1, and that's going to be the first part of what we've got. Our y value is going to be what we get when we plug -1 into our original equation. So that's going to be, let's see, -1 plus 3, because -1 squared, plus 2. So this comes out to 4. And then our slope is y prime of -1, so that's up here, 3x squared plus 6x. So that's going to be 3 minus 6 when you plug in -1, which is -3. Our equation is then y minus 4 is equal to -3x plus 1. When I look at all my possible answers, I see that none of them are in point slope form, so I just need to manipulate a little bit. When I distribute -3, I get -3x minus 3. And then add 4 to both sides, and I'm going to get -3x plus 1, so it looks like our answer is B. All this is just review finding tangent lines. Once we have found a tangent line, we can use it to approximate a value that is close to the value that we used to make the tangent line in the first place. So if you look at example 3, we've got a function value. We're going to write our tangent line at x equals 2, and then 2.3 is close to 2, so it's probably going to give us an estimation, remember like this, an estimation that's pretty close to the actual function line. So let's start with the tangent line. We've got an x, a y, and a slope that we need. So our x here they gave us was 2. Our y is going to be what we get when we plug into, which is 8 minus 4, so our y value is 4. And then our slope, well, we'll have to take the derivative. F prime of x is equal to 3x squared minus 2. When I plug in 2, that's going to give me 12 minus 2, so our slope is 10. So the equation of the tangent line is y minus 4 is equal to 10 times x minus 2. Sorry about the handwriting. The last part now is actually, in my opinion, the easiest part. They want an estimation of the function value at x equals 2.3. Well, we're going to plug it in right there. 2.3 is close to 2, so I'm expecting that a y value that we get is going to be close to 4, because whatever this is, it can't be too far away from the point that we actually used. But we'll see. So y minus 4 is equal to 10 times 2.3, 10 times 2.3 minus 2. And I'm just going to type this into the calculator. I know I could probably do it in my head, and then add 4 to get what y is. So 10 times 2.3 minus 2, and then adding 4 to that comes out to 7. So I take it back. This isn't super close to 4, but that's the estimation that they asked for. And that's it. Last example for this video, you notice this is the situation I was talking about. They gave us information, but we don't have a function value. So we're going to have to use this information to approximate what the actual function might be. So let's start with our tangent line. We know that our x is 6 as given by both of these. Our y is 4 because that's what that means. And then our slope is -1 because that's what they said the slope at 6 was. So we can write our tangent line as y minus 4 is equal to negative x minus 6. Now they're asking us to plug in 5.9. So we're going to say y minus 4 is equal to negative 5.9 minus 6. I'm gonna do that, negative 5.9 minus 6. And then after I do that, I'm going to add this 4 to the other side. And that comes out to 4.1. And this is what I was talking about in the last example. You often get similar y values to the point at which the tangent line was drawn.